So thank you everyone for coming to this week's workshops for the Coding Outreach Group's summer workshop series. This week we have Jeremy. He has very kindly volunteered to do a little introduction to Markov chain Monte Carlo algorithms. It's a bit of a Bayesian prerequisite here, but I think Jeremy will kind of steep us into it. Jeremy, I actually went through your LinkedIn. So you graduated with your PhD from Utah State University?
Yes.
Yes, okay.
Interesting. Oh,
Go ahead. No, go ahead.
I was just going to say, everything I do now is like with people. My PhD was all rats.
Oh, wow.
So,
Yeah.
uh, yeah,
So a bit of a 360 here.
yeah,
Um,
quite a bit
and
different.
and so you taught a lot of stats there, but now you work with Tom Molino, our resident stats expert, working on his R1 longitudinal data. So I'm sure you have a lot of differentiating statistical experience. And we're really excited to have you do this workshop. It'll be a fun one, I think. So from here, I think you could take it away.
Oh, well, thank you. Um, yeah, so I'm Jeremy. I work with Tom, and today I'll show you all about programming a Metropolis MCMC. The biggest benefit to using one of these MCMCs is for Bayesian modeling. And so I'm going to start off with kind of an introduction to Bayesian modeling. It will be very much a crash course. So yeah. And I cannot stand to listen to my own voice, so I am going to I'm not going to play the video. I'm actually going to go through this. Oh, wait, let's switch these. Right, okay. Is that what I need to do? Yeah, that'll work.
Looks good.
Okay. So, real quick, I'm just going to talk about why we use MCMC. There's a lot of different applications for it. It's not just Bayesian modeling, but this is where it is very frequently used. So I do want to talk a little bit about Bayesian modeling. Again, that's going to be a crash course. Then I'll briefly talk about what an MCMC is, very broad terms, and then introduce what a Metropolis MCMC is. And then, of course, the biggest reason why we're here is actually implementing and programming one of these MCMCs. All right. So we use MCMC, at least with Bayesian modeling, because we're performing some sort of quantitative analysis. And regardless of which framework you're using, frequentist or Bayesian, our ultimate goal is to estimate parameters and draw some sort of inference from samples of data that we collect. With Bayesian parameter estimation, we are typically focused on estimating the probability of a parameter given our data, given the sample of data that we've obtained. And generally speaking, we're not interested in just a single parameter value. We're actually interested in the probability of a range of parameter values. And so we represent this with a probability distribution. This is a little bit different than the frequentist framework, where we're just generally focusing on the point estimates. Here with Bayesian estimation, we actually estimate a probability distribution. So we might be interested in looking at mean differences in a population. So for example, does acceptance and commitment therapy reduce anxiety? Given that we have some sort of mean difference in our sample. So given that we found that ACT therapy reduces anxiety in our sample, how can we generalize that to the population? And again, this is generally what we're doing in the frequentist framework as well. Oh, and I wanted to add, I should have said this at the very beginning. I do not mind if people interrupt me. So if you find something that you're like, oh, I want to ask them about it, feel free to just interrupt or toss a question. Totally happy for that. All right. So if you're familiar with Bayesian modeling, just generally speaking, you might have seen this equation. So this is Bayes' rule. We have theta as our parameter of interest, and then y as our data. On the left-hand side of the equation, this is what our goal is to estimate. So it's the probability of the parameter, and again, we're generally talking about a range of parameter values given our data. And so you'll see this called the posterior distribution. And with Bayes' rule, we can estimate this posterior distribution. So on the right-hand side in the numerator, we have the likelihood. So this is the probability of our data given a parameter. And this is the most closely related aspect of the equation to a frequentist framework. This is actually what we usually estimate when we're using frequentist statistics. And now the likelihood is multiplied, or you'll often see this term weighted by the prior. And this is just the probability of the parameter value. And you can think of this as what are some plausible values for the parameter before we've even seen or observed the data at all. And then all of this is divided by what is called the marginal distribution. Another term for it is the evidence, and this is just the probability of the data. I'm going to talk a little bit about some of these in more detail. The first one I want to talk about is the prior. Now, priors are often a source of interest when people are approaching Bayesian modeling. One interest is it seems very beneficial to be able to incorporate prior knowledge in our analyses. However, priors are also considered a source of controversy in Bayesian modeling. And I think this paper by Garcia Perez summarizes it very well. So essentially in this paper, they suggest that whenever we use really informative priors, mathematically speaking, this is very similar to literally just creating more data and inserting it into the model. And obviously that's, creating new data and making our sample size seem much bigger is inappropriate. And so I do think that is a cause, at least for pause, whenever you're using your priors. So you should be very careful and very mindful with how you use your priors. That said, there are several benefits to using priors. So again, the prior is the probability of the parameter before you see the data. Like I said before, we generally represent this as a probability distribution, and this helps simplify a lot of things. Because instead of having to specify the probability of every single value of the parameter, we can just say, look, it looks like this probability distribution, and that makes our life a lot easier. And again, we're answering the question, what are just some plausible values of this parameter? Just generally speaking. And so here I have the example of IQ scores. Now, we know based off of how IQ scores work, they follow, let me get my laser pointer here. They follow a normal distribution with a mean of 100 and a standard deviation of 15. Now, we could use a uniform prior, and this is basically what we do in frequentist framework. And let's say we're estimating the mean IQ of a sample. Well, if we're using a uniform prior, we're essentially saying that the probability of getting an IQ score, or the average IQ score of 55 is equally likely to getting an IQ score of 100. But we know that that's pretty unlikely in terms of IQ scores. that just before we've even seen some data, we know that that's a pretty unlikely scenario. And so we could just provide a very weakly informative prior. So here in the yellow here, I have a normal distribution with a mean of 100 and their standard deviation of 40. Now, this is very weakly informative because you'll notice that it doesn't follow the actual strict IQ distribution. But what we're basically saying is, okay, an IQ score of 100 is more likely than an IQ score of, let's say, 55 or even 70. But we're not saying it with a high degree of confidence because we want our data to really govern our estimate here. And this has a very practical benefits. So it helps improve our estimation, particularly when we start using MCMC, because the MCMC is going to sample repeatedly from a probability distribution, and our priors can help that sampling so that we don't get stuck somewhere really weird. So for example, if we use a uniform prior, it's possible our MCMC might get stuck in this region that's pretty unlikely that we know. But if we have just a weakly informative prior, we can help gravitate the estimates that we're drawing in the MCMC to be a little bit closer to this mean of 100. Again, we're not stating it with a high degree of confidence. We're just kind of helping the MCMC not get stuck in some of these weird places. It can also be used to incorporate conservatism. You'll often see the phrase regularization. And the way priors can help us be a little bit more conservative about our inferences is, let's consider a beta coefficient from a regression model. So a beta coefficient of 0 means that there's no effect. If it's greater than 0, then there's some positive effect. Negative beta coefficient, there's some negative effect. And if we set a uniform prior, we essentially say, okay, any beta coefficient is possible from our data that we're going to estimate. But let's say we want to be a little more careful with our inferences. If it's testing a new drug or something like that, that you want to be more confident that this has a very strong effect, you might want to use a prior such as one centered with a mean of 0, so centered around no effect, with some standard deviation. I'm not going to worry about that for the moment. And essentially what you're saying is you're going to let your data inform your estimates of this parameter, but you want to be a little bit conservative. You want to draw it a little bit closer to 0 because there's a high cost with suggesting that this effect is higher than you really want to say. So those are just some of the benefits of priors. Okay, now let's get back to Bayes' rule real quick. So on the numerator, we have the likelihood weighted by the prior. This is referred to as the joint distribution. And there's an issue with the joint distribution, and that issue will become apparent in just a little bit. So the joint distribution does not integrate to 1, which means that it is not a probability distribution, and we cannot interpret this distribution on the probability scale. And this is why we need that denominator, so that marginal distribution. Again, this is the probability of the data. And really, all the marginal distribution does is that it normalizes the joint distribution and basically turns it into a probability distribution. The problem is that although with simple models, we can compute the marginal distribution analytically, that is, we can just use math and algebra and whatnot to compute the marginal distribution. With complex models, this is effectively impossible to do. It becomes too complex. It would take an enormous amount of time to do. And this is what has prevented Bayesian modeling from really growing for quite a long time. But there is an important aspect of this. So again, the marginal distribution, that denominator, is effectively a constant. It's just a scalar. Again, all it does is it helps the joint distribution integrate to 1 so that we can interpret our posterior distribution as a probability distribution. And so if we recognize that the marginal distribution, all it is a constant, we can actually simplify Bayes' rule a little bit. So we have the full equation here up top. And if we remove that marginal distribution, so the denominator, we can simplify this to say that the posterior distribution on the left is proportional to the joint distribution on the right. Now, we haven't solved every issue because all we've said is it's just proportional to. We still need to figure out how to get this joint distribution to integrate to 1. Okay. So here I have my little graphic, joint distribution at the top. We're trying to get to that posterior. What we're going to do, one way to get the joint distribution to integrate to 1 is that we're going to sample from the joint distribution some number of times that we're going to specify, that we know. And this allows us to generate a frequency distribution. And we can generalize that frequency distribution to a probability distribution. And that's how we get from the joint to the posterior. Now, we just need to figure out how we're going to sample. And this is where MCMC comes into play. This is what has really unlocked a world of Bayesian modeling for us, is being able to sample using MCMC. All right. So let's transition into what is MCMC. I can never remember what the acronym actually stands for. So if I don't have these words in front of me, I will almost certainly screw it up. So it's Markov chain Monte Carlo. MCMC is a very broad term. It just refers to a set of algorithms that we can use to draw samples from a probability distribution. And for our purposes, we're really interested in drawing samples from the joint distribution. When the MCMC gets to an equilibrium point, so when it doesn't bounce around quite a bit, and we'll see that later on, what that actually looks like, it will resemble that target probability distribution. And that's how we can get from the joint to the posterior. And weirdly enough, we can actually sample from the joint distribution using MCMC without actually having to fully specify the target probability distribution, that is the posterior. And today, I'm going to show y'all how to go through a Metropolis Hastings MCMC. I also write Metropolis. They're kind of, I guess I should give Hastings credit as well. This is considered a quote-unquote simple MCMC. That's arguable. I know MCMC is simple to me, but I'm sure others might disagree. And generally, we'll go into the specific steps of this, but generally what we're going to do is we're going to generate candidate values of a parameter.
Sorry, I was just saying, most other people I saw online also cut Hastings out and then didn't give him credit, so I don't think you're alone.
Yeah, poor Hastings. I guess that happens. But so generally speaking, what we're going to do is we're going to generate candidate values of a parameter. We're going to do this with a Gaussian random walk. We're going to decide whether or not to accept this candidate or we're just going to retain the previous value of the sample. So this will be our parameter of interest. And then we're just going to repeat this over and over.
Could I ask a quick question, Jeremy?
Yeah, what's up?
And you might not, this might be beyond this, but I know I've never done MC prior to this tutorial, but I have like seen Markov chain modeling in neuroscience, usually like referring to trying to model transitions from one state to another, like activation of this network to activation of this network. Is the Markov chain part of this name that those like last two bullet points, like the deciding whether to accept and then moving on and resampling, or like, do you know like what part of this makes it Markov chain, I guess is what I'm asking?
I do whenever I look this up, which
Okay.
is once every 6 months.
Sure.
Yes, I do believe the Markov chain refers to basically an autocorrelated sampling process.
Mhm.
And if I remember right, Monte Carlo just means that it's random sampling.
Okay.
Which is weird to say because it's autocorrelated.
Sure. Seems
And
like a little paradoxical, I guess, but
it does. And I think I think who was it? It was Stanislaw something or another that developed MCMC. And he was a theoretical physicist, so I suppose it makes sense there. And he was, I believe, trying to model processes involved in some weird random process that was still autocorrelated in physics.
okay.
Which is interesting how it becomes applied here, but yeah. But yeah, you might have to Google that for an exact answer, but I think that's what it has to do with.
That's fine. I was just curious. Yeah, thank you very much.
Yeah. Oh, okay. And then, yeah, so I have the steps here, and we'll actually see this in the code. So I do want to kind of go through these a little more in detail. So at the very beginning, we do have to choose an initial value for the parameter. So this might be our intercept term when we're getting to the regression model. And we'll call this theta 0 or theta naught. All this is just to get the MCMC going. Because if you remember, we are deciding whether to accept the candidate or retain the previous sample. But we need a previous sample to begin with. And so that's why I call this step 0. Next, so when we actually get in the MCMC, we're going to propose a new value for the parameter. We're going to do this with a Gaussian random walk. And again, I'm going to walk through all the code for all of this, but just to kind of get this in the back of your head so you know, generally speaking, what we're doing. So we're going to propose a new value, and we'll call this the candidate, so theta star. And then we're going to use Bayes' rule to calculate the probability of that candidate value for the parameter versus the probability of the previous value in the sample. And the reason why we're going to calculate these probabilities is that we're going to use that to determine whether or not to accept or reject that candidate. This acceptance probability is determined by R, which is the ratio of these probabilities. And if you think about the mathematics of it, so just think of this as the probability of the candidate versus the probability of the previous sample value, previous parameter value that we've been working with. If R is really high, if it's greater than 1, that means that the candidate is much more likely than the previous sample of the parameter value that we're considering. If R is really low, so if it's below 1, this indicates that the probability of the previous sample is much more likely than our candidate. That makes sense how what R kind of means, broadly speaking. It's kind of like an odds ratio might be one way to think of it. Okay. And so in our third step, we're going to use a decision rule to determine whether we're going to accept or reject the candidate. If we accept the candidate, that becomes the next sample in our posterior, and we're going to go about our business. If we reject it, again, we're going to retain the previous sample. We're not going to consider that candidate again. And the rule to determine whether we're going to accept or reject this is that if the ratio of those probabilities is greater than 1, so again, if the probability of the candidate is higher than the probability of the previous sample, we're going to automatically accept that candidate. That's going to be put into our MCMC chain. And really what we're building in the MCMC chain is our posterior distribution. If we do not automatically accept the candidate, so if R is less than 1, we're still going to give it a chance to be accepted, which might seem a little bit weird, but we're going to give it the chance to be accepted with a probability of R, so with the probability of this ratio. Now, a very common question is, why wouldn't we just reject it automatically? If, you know, why aren't those reciprocal decision rules? The reason for this is that if we automatically rejected low probability candidates, then we would not sample from the, if we're dealing with like a normal distribution, we wouldn't sample from the tails of that distribution. We wouldn't really fully characterize what are some of the low probabilities of that parameter value. But we do still want to characterize that part of the distribution. And so that's why we have this decision rule, which seems a little funky. Okay. And then we're just going to repeat this n number of times. So we're just going to go back to step 1. All right. Now let's talk about how we're actually going to implement this thing. So I'm going to get to the code in just a second, but just to introduce some of the example and then some of the practical things, I wanted to use something. When I was first taught this, I think, what was it? It was, we were estimating how many seeds are in different, what was it? Different types of plants or something like that. I took this in the ecology department, so it was super tangential and difficult for me to understand. So I'm gonna use an example from something that I study. So here I simulated some data, economic demand data for people using fentanyl and who've been using fentanyl for some number of years. The dependent variable, I'm only going to describe very broadly. I have the specific details here. It's called elasticity of demand. This is just a measure of demand or preference for fentanyl. And the long and short of it is that a higher value for elasticity means that the individual is less addicted, and a lower value means that the individual is more addicted to fentanyl. There's a lot more to do with elasticity, but that's how we can kind of interpret it. And technically speaking, we'll actually be working with log elasticities because those would not be normally distributed unless we logged them. And then the independent variable is the number of years using fentanyl. And so we might expect that as somebody uses fentanyl more across their lifespan, they might be more addicted. So their elasticity might be lower. Okay. And then if you're interested in more of this, Hirsch and Silberberg, very important paper on behavioral economics, at least in my opinion, talking about this stuff. Do you have any questions about the data at all? Okay.
Does everyone have the data downloaded? Did anyone have any issues getting that set up on your RStudio or anything? Okay.
Sweet. Okay. And then just a couple quick things. So there's going to be one spot where I'm going to show a long and a short form of code. The reason for that is whenever you see MCMC, they'll use a very odd set of code to represent how we're going to accept our candidate or reject it. And so I also have a long form of code. What y'all have is the concise short form, but just to illustrate what that's actually doing, I'm going to kind of deviate real quick from it. We're going to estimate, and I should have changed this. We're actually going to estimate 3 parameters. So we're going to estimate an intercept, slope, and a variance. And we're going to do this we're going to go through steps 1 through 3 here on the right, every single iteration for each parameter. And we're going to do this for each parameter sequentially, such that when we're focusing on one parameter, the others are going to be treated as quote unquote known. I think this will be more clear in the code, but just to kind of preface that. And then finally, we're going to be working on log space. And this just avoids weird issues where if you multiply tons of probabilities together, you get tiny numbers. Working on log space helps us avoid that. But that does mean that we have to be mindful of our laws of logs. In particular, the log of, let's say, x times y is equal to the log of x plus the log of y. And then likewise, log of x divided by y is equal to the log of x minus the log of y. Just something to keep in mind when we're going through the code. Okay, so that's the end of the intro and whatnot. Hopefully y'all are still awake with me talking about all that. All right. So, let's see. All right. Am I still sharing my screen and all that? Okay. Okay. All right. So we just went through this video. And I'll get to my specific code, but because this presents all the fancy equations, we'll go through this. So yeah, make sure to load the packages, the data. I simulated these data and there is code for how I simulated it. I do think that's an extremely useful thing to do is to simulate data for your models, because it helps you understand what are you assuming about your data and what are some of the constraints that you're actually putting on your data. So the data set, like I said, is economic demand. And it's a data frame with an ID column. There's years using fentanyl. There's sex. So I think 0 is female, 1 is male. And then log elasticities here on the right. Here's a scatter plot. So kind of what we were predicting, that we have elasticity as a function of how many years somebody's been using fentanyl. If somebody's been using it more across their lifespan, their elasticity is lower, which again means they're more addicted. Here's a histogram. I'm not gonna, just nice to show a histogram. Same with some summary statistics. We don't need to go into a whole lot of details here in particular. But this is where we want to get into. So we do need to specify each part of our model. And really what we are technically doing is we're specifying the model that we assume generated these data, which is kind of a weird thing to think about, particularly in terms of regression, because you might be like, wait, did a regression model actually generate these data? Richard McGilrath has a lot of very interesting discussion points about that. I highly recommend his lectures on regression and whatnot. Long story short, he recommends using theoretical models, but if you don't have a theoretical model, regression does pretty dang good. Okay, so we have our observation is equal to an intercept term, so beta naught, plus our slope coefficient times the predictor, so xi, and then some random error, where that error is normally distributed around a mean of 0 and some variance. This is going to be another little bit of a weird way to think about the model we're using, but it will help us later on. So we could alternatively say that our observations are normally distributed around the predicted values of this regression model with some error associated with it. It's an equivalent way to state what we have up here, essentially. And, oh yeah, so we have three parameters that we're going to estimate. So an intercept, a slope coefficient, and a variance. Because R uses functions that take standard deviations, we're just going to worry about the standard deviation. We're just square rooted. So these are the parameters that we are estimating. And this is our ultimate goal. This is the posterior distribution. And we're going to do this with Bayes' rule, which we have here. But remember, we do not need the marginal distribution on the denominator. So we're going to sample from the joint distribution here on the right. All right. So this is the model that we want to get at. So we need to specify our likelihood and our priors. So with the likelihood, we're specifying the probability of our data given the parameter values of interest. So the intercept, slope, and standard deviation. And effectively what we're doing is we're saying we're going to propose a value of these parameter values, or parameters, sorry. We're going to propose a value of these parameters and say, all right, what is the probability of these data, the joint probability of all these data if we have this value for the intercept, slope, and the standard deviation. And when I say joint probability, it just means they're all multiplied together. What is the overall probability? And we can do this actually in a very simple way in R. It's simpler than I ever thought it was when I was introduced to this kind of stuff. So we're just going to use the dnorm function. Dnorm technically works with probability densities, but we're working with a continuous variable, so it works out just fine. Dnorm takes x. X is actually going to be our y. So this is our observation. This is what we want probabilities for, according to some mean, standard deviation, and then we can specify this is the default in dnorm is log equals false. We're going to change that to log equals true. And you'll notice that what that does is now we need to sum our log probabilities. We're not going to multiply them anymore. And you'll see this in the code. And because we're going to do this for each iteration of the MCMC, we're going to toss this into a function. This just compacts everything, makes it simpler for us. So in the function, we're going to pass our data. So the y, our predictor, the values of our predictor. So this is the years using fentanyl. The intercept, the value of the intercept that we're interested in calculating the likelihood for. Likewise for the slope coefficient and our standard deviation. And again, we're using the dnorm function. So we're passing our data that we want probabilities for. Again, we're just inserting we're using the predicted value as the mean here. So we're doing our intercept plus the slope coefficient times the predictor with standard deviation of sigma, and then we're specifying log equals true. When we pass the log elasticities, so y, and the x's, so the years using fentanyl, these are vectors. The parameter values, those are just going to be single values that we're going to pass to this function. What that ends up resulting in is the probabilities of those data given the parameter values, and that's going to be a vector because we passed a vector of data and a vector of those values for the years using fentanyl. And again, we want the joint probability of all of those things. And so we're actually going to sum all of that to get a single number. And the summation is because we're working on the log scale. How's everybody feeling about the likelihood, the log likelihood technically?
I think
Decent?
the script is very well commented. I was thinking that while we were putting it up, so I appreciate that.
Cool, cool.
Definitely helps with the understanding.
Right.
Yeah.
Cool. Glad it's helpful. Okay, and then of course the last thing we want to do is actually return that stuff. Normally I use a different word instead of stuff, but I think maybe not the best context. Okay, so now we want to specify our priors. Here remember we're calculating the prior probability of a given parameter value independent of the data. Before we've even seen the data, what are the probabilities of some intercept value, some slope coefficient, and some standard deviation? Again, the easiest way to represent this is with probability distributions. Here I'm setting very weakly informative priors. I'll talk about this very briefly in a little bit, but the degree to which your prior is informative or not does depend on the scaling of your data. I'm going to avoid that issue at the moment, but that is something to keep in mind. For these data, the priors I've set are very weakly informative. So here for the intercept, I'm setting a normal distribution with a mean of 0, standard deviation of 50. Likewise for the slope coefficient. And then for the standard deviation, I'm setting a half Cauchy distribution that has I think, does it take a standard deviation? It might be a location or a spread parameter. No, it is a sigma. We'll see in a second. The half Cauchy is a Cauchy distribution that you just cut in half. That's all it is. And you cut in half at 0, and you say only positive values are plausible. This makes sense that we'd want to use this for a standard deviation because standard deviations can only be positive. And so that's one of the ways in which we can actually kind of help some of this estimation. We can say, well, we already know that negative values aren't plausible, so why even consider those? Those have 0 probability. And then it is very wise to plot the assumptions of your priors. And there's a couple of ways to do this. I'm going to show 2 of them that I like. One is to literally sample from your prior. So the way I do that here, so this is for the intercept, I'm going to use the rnorm function. So this is generate random samples from a normal distribution. It's 1,000 samples, and that distribution is given by a mean of 0, a standard deviation of 50, and then I'm just plotting it. And this is what our prior is. This is kind of what we're assuming are some plausible values for our parameter of interest. Now, because I know these data, I know that this is very weakly informative. The spread of this is huge for log elasticities. It's centered around 0, but a value of negative 50 is not extraordinarily unlikely, according to the prior, that is. And then we could, again, I'm showing a couple of ways to do this. We could also actually plot the probability, because this is just a frequency distribution. We could actually plot the probability, and that's what this function does right here, or this code does. And here I'm just using the dnorm function and give me the probabilities of values of the intercept from -200 to +200 according to this distribution. And we get something that looks like this. Just another way of representing what I did above. I will say this. If you ever use hierarchical Bayesian modeling and you have to specify priors, I find that this sampling from your priors is a much easier way to go about doing a lot of this. Because here you really don't need a lot of mathematics. You can just literally sample from it. Once you start using, let's say, the dnorm function, you kind of have to start understanding some of the mathematics behind your priors, and that quickly gets out of my wheelhouse. So we use the same prior for the slope coefficient, so this shows the exact same thing. For the standard deviation, I'm just randomly sampling from the half Cauchy distribution. One thing that's aggravating with the Cauchy distribution is that values that are really high get sampled every now and then. So you get a histogram that looks like this, that's not very helpful. So you might need to subset your data. And that's basically what I'm doing here. I'm saying, okay, give me the values, the distribution of the standard deviations that are under 200. And let's check out that histogram. And this was what that looks like. And this is generally speaking what we want to see. So a standard deviation 50 is pretty high for these data. And again, this is what we're assuming are some plausible parameter values.
Sorry, Jeremy, could I ask, that 200 number that you settle on for that, is that just sort of like eyeballing it, or is there
That's purely eyeballing it.
Okay.
Yeah. I think I had to choose a few different ones, to be honest, to do this. So yeah, just a weird thing, and this will be kind of aggravating, is there is a lot of parts of this that are just kind of, you have to tinker with it. And that can also be very frustrating when you're first starting out because you don't know how to tinker with it, because you don't know what's inappropriate to tinker with. And as you do it more and more often and you start reading more about this, you'll get more acquainted with it. So yeah, that was just eyeballing.
Okay, no worries. Just check.
No, great question. This again is just another way of showing this, of this Cauchy, half Cauchy distribution. This is a little bit nicer. You also see I put a half normal, which is also a very plausible distribution to use for standard deviations. I just used the Cauchy because you'll see that in the literature. I remember wondering what the heck is that. So here I just plot a half normal in the red here. You'll notice that the Cauchy puts a little more weight in the tails, so it considers larger values for the standard deviation.
Real quick, technically not a stats question, but an R question. So this is for anyone who might be able to help. So I have that line that you have there. When I have a plot and then I don't have a plus after that like type line, I get an error. I don't get it to plot. I have to like add the lines command to the plot to get it to graph. Is there a reason? Like, do I have my RStudio set up incorrectly? Or is that like...
I didn't even know that the plus would work for that.
Yeah, it'll add it
So
onto the plot.
if you run them all together in the same line, it should work. Like,
do I have to run the chunk and not like by...
yeah, that's generally. Can you see my code?
Yeah.
Yeah, we can see that.
Let's let it run real quick. Yada yada yada. So yeah, if I run it one at a time, it'll throw an error. But if you run them at the same time, it should do that. And yeah, if you run it as a chunk, can you do the plus?
Yeah, the plus
Yeah.
works.
I think a plus should be effectively the same thing as highlighting both of them.
Oh, I
It
didn't
just
know
it just
that.
tells our like wait before you process this.
Okay, yeah, I wasn't sure. I was like, because I've seen that before, and I guess I just run line by line, which I shouldn't be doing.
Yeah.
No,
Now,
that's how I generally do it.
Yeah.
that's right. Like you see that a lot with like ggplot code and stuff
Yeah.
too, where like it needs to get the whole chunk or whatever. Yeah.
Hmm.
We all learned something.
I didn't know that worked with the base plot function. Cool.
Yeah.
Okay. For the sake of time, I'm going to kind of gloss over the consideration for priors. I'll kind of leave that for tinkering with. Basically, this section is just presenting the idea that you can change these priors to a lot of different values. In particular, it's interesting to set a more informative prior. So I do that by lowering the standard deviation. And this is where I do that with the intercept term. So this is with a much more informative prior on the intercept term. And I'm keeping the same x-axis. And you'll see how tight that prior is. And keep in mind, this is what you're assuming is before you see the data, this is what you think the parameter value, the range of parameter values is. Again, I'm using the same x-axis when we had the very weakly informative prior. If we look at it a little more zoomed in, so we look at this distribution, it doesn't look quite as tight. So you do have to pay attention to those x-axis ranges. And yeah, that's generally what this section highlights. So this is for a more informative prior. And again, this is just different ways to show the same information. We could also suggest a uniform prior. So this is just any value is plausible. So a uniform prior, you basically say positive or negative infinity is possible. R doesn't let you do positive or negative infinity. So I just put negative 10,000, positive 10,000. And what you need to think about with your data is that realistic? I know because I know these data, I know that's totally unrealistic, these values for, let's say, the slope or the intercept. And so that's something to think about with your priors, is that you're kind of making some assumptions about your data. And you also know something about your data as well. So I write here that SAT scores have a minimum of 400. So if you're estimating the mean of SAT scores, you can specify a prior that says means below 400, below the minimum, are impossible. And that's perfectly fine to do because that's literally impossible. And you don't want to slow your MCMC down for something like that too. So, okay. That's my rant about that. Okay, and so this is how we're going to throw our priors or program our priors. So again, we're doing this as a function. And so here I have the prior for the intercept. In the function, we're giving it a single value for that prior. This is just going to be one value for that prior. We have our mean for that prior, so 0, standard deviation of 50. And this is what we saw before, as in the likelihood, we're saying, what is the probability of that parameter value given this mean and standard deviation? And again, we want to set our logs to true because we're working on the log scale. And we're going to return that. And the exact same function for the slope coefficient, and a very similar function for the prior on our standard deviation. But instead of dnorm, we're using dh Cauchy. There is also a dh norm as well, so you could also play around with that. Okay, so let's actually get to the code. And yeah. because I think, so after we've specified all this stuff, so let's actually talk about building the sampler. We haven't even gotten to the sampler, and I've already been talking for an hour. Apologies. I won't shut up if you give me the option. Okay. So we need to build our sampler. Remember those steps. We have technically four steps. We have a step 0, but we have steps 1 through 3, and we're going to do this iteratively in a loop is what it ends up being. So we obviously, because we're drawing random samples, we want to set our seeds so that we can reproduce these results. We're going to specify the number of iterations of our MCMC chain. So in this case, I specified 20,000. That's pretty big. I don't know if there's a hard and fast rule. Generally speaking, if it's a difficult model to estimate, you might use a higher number of iterations, but of course that takes longer. And then we have 2 sets of tuning parameters. This is what we're going to use for our Gaussian random walks. I'll talk a little bit more about this later on. Basically, we just need to specify these so that we can generate candidates later on. So here I use a tuning parameter for the intercept and standard deviation as 0.5. And because my MCMC did not work very well with that tuning parameter for the slope, I changed it to 0.05 for that slope. And this has to do with the scaling of the years variable. Here I am creating an empty data frame to store our posterior distribution. And so we're going to have, what is that, 7 columns. So we have our iterations, 1 through 20,000. This line of code just says create a vector of this length, and it's going to be numeric. Doing that sets all those values to 0, and that's perfectly fine. This will be important later, but we do want to determine whether candidates are accepted or rejected on each iteration of the MCMC. And so we will have, those will be automatically set to 0, which means they're rejected, and we will fill them in with 1s whenever they're accepted. Okay. Now, if you'll remember, step 0 for each parameter is to choose an initial value. So here I'm just accessing the first element in the intercept column, the slope column, and the standard deviation column. I'm just generating a random number. This could be honestly anything. It just needs to be something reasonable. And in fact, if your MCMC is good, it'll get away from the unreasonable values. So, yeah. You'll notice, so we have our initial values for these parameters thrown right in here. So we basically already have iteration 1 specified for these parameter values. And then to make our code a little more efficient, we'll just calculate the likelihood of those initial parameter values. This is using that calculate likelihood function. Here, I'm passing the data that we want our probabilities for, given our parameter values. And remember to use that slope coefficient. We also need our predictor value. So this is the years using fentanyl. So I ran that code. So the log likelihood of these data is some huge negative number that, because it's on log scale, we don't know what that means, but that's perfectly fine. You could exponentiate it. Let's check that out. So likelihood. So R can't even process it as 0. This is why we work on the log scale, because it's too small of a number to even worry about. Okay. So now we actually get into the MCMC. I like to do my loops. So we're going to do this with a for loop, as you may have guessed. And we've already specified the first iteration, so we're going to start on iteration 2. And when doing this, I like to literally specify I equals 2, just so we can kind of see what's happening step by step by step for each of these parameters. So again, we do this, we go through steps 1 through 3 for each parameter value sequentially. So the first parameter value is the intercept that I'm going to focus on. So this is beta naught. Step 1 is to propose a candidate value. We'll do this with a Gaussian random walk. So that means a random number from a normal distribution. We just want one random number. So we have n equals 1. And the mean of that distribution that we're going to generate this random number from is based off of the previous sample value. So this is, if we think of what this intercept term is, so I is 2. So this is the first iteration of the posterior. And we're basically just going to pull this parameter value. That's what we're going to use as the mean to generate a candidate. And then the standard deviation is the tuning. This generally governs how far our candidates go from sample to sample. We'll see this in the trace plots later. So generate a candidate. So the candidate is negative 5.39. That's not too far from the first value here. Next, we're going to calculate the likelihood of that candidate value. So this involves the same function as before, but now we want to calculate the likelihood for this candidate value. So we're focusing on the intercept, and so that's what's going to go into this intercept part. We hold the other parameters constant. So we're going to use what's already in the previous sample or previous part of the posterior distribution for the slope and standard deviation. We'll run that. Our candidate likelihood is this negative number that again is kind of hard to interpret. And then here we're going to use that basically Bayes' rule to calculate the joint distribution that I talked about before. It's that numerator in Bayes' rule. We don't have to worry about the denominator because we're using MCMC, and also because we're calculating a ratio. So here I have the current value in the posterior distribution. So we already calculated that likelihood. We need to calculate the prior probability of that parameter value. So I'm just spitting that previous value for the parameter in that prior beta naught function. We're calculating that. We're doing the same thing for the candidate. So we're calculating the probability of the candidate. And then we need to calculate our ratio of probabilities. Remember, we do this by calculating the probability of the candidate divided by the current or previous value in the sample. With the log scale, we're going to subtract these. So we're going to subtract these log probabilities and then exponentiate that. And that helps us put it back on the probability scale, kind of. So we'll calculate R, and our R value for this candidate is 28. So what does that mean for this candidate? It's going to automatically be accepted. Right. No worries, CM. It's going to be automatically accepted because it's greater than 1. And this is where the decision rule is. This is a very weird set of code. And so this is the concise, the short form of the code. we're going to take a quick look at the long form of what this code does. So remember, we have our R value. According to step 3, if R is greater than 1, we're going to automatically accept it. So our decision is accept. If R is less than 1, then we're going to accept the candidate with probability R. And that's what this code does. So it determines whether we're going to accept or reject this candidate value with probability R. Hopefully this isn't more confusing than the other code, but basically we're saying decide whether to accept or reject this value with acceptance probability of R and a rejection probability of 1 minus R. And just pick one of those according to those probabilities. If our decision is to accept, then the next value in our posterior is going to be the candidate. We're going to specify that we accepted that candidate value. So accept underscore beta not equals 1. And then we're also going to update our likelihood with the candidate value because it was accepted. If it's not, if we decide to reject the candidate value, then we're just going to retain the previous value of that posterior and nothing else changes. We've already filled accept the intercept as 0 column, or the accept intercept as 0 column as 0, sorry. So we don't need to worry about that, and our likelihood stays the same. The way we're actually going to implement this is this weird set of code. This does functionally the exact same thing. This is what you will more frequently see. And for the sake of time, I'm not going to really go into the details of what this exactly does. And I hate giving that answer, but it does what we just went through. And you might just test it out and see what happens. Okay, so after we decide whether or not to accept or reject, I think I already ran this. We're going to move on to the next parameter value. So in this case, the slope coefficient. And it's the exact same process. So step 1 is propose a candidate value. Remember, I had to use a different tuning parameter. So that's the only thing that differs here. But we're basing the mean off of the previous sample for the slope. And then with the candidate likelihood, it is important that we get this code right. So we still pass the data in the years using fentanyl, just like we did before. But now we're using the updated value for the intercept. So this is the most recent value. For the slope, we're using the candidate. So this is the candidate likelihood. Because we have not updated standard deviation, we're still going to use that previous value. I can't remember, I did not run that code. And then again, we're going to calculate our joint probabilities. So we'll run this code, calculate R, run through steps 1 through 3. This is all exactly what we did before. Updating sigma is basically the exact same process. There is one little difference that's a little bit odd, but it works out fine. So we're still going to use a Gaussian random walk to generate candidates for the standard deviation. But remember that candidates or that standard deviations can only be negative. And so we don't want candidates that are negative. And with this line of code, that is possible. So we want to avoid that at all costs. And the way to do this is that if the candidate is less than 0, it's automatically rejected. The probability is 0. So that's what this line of code here does. If it's greater than 0, we're in the clear, and we're going to go through steps 2 through 3. And those are exactly the same that I showed before. So that's the only big difference here is that if you get a candidate that's less than 0, you're just going to reject it automatically. How do y'all feel about the Metropolis sampling?
So when you do it when it's less than 0 and you do accept, but you add the probability to it, is that where when you don't have informative priors where it'll get really stuck because it starts adding in all these kind of, you still accept it, but with that added probability, so it's kind of introducing a lot of information, or is it get stuck other places?
Do you mean like here?
Yeah.
Yes, yeah, so essentially, I have to think about that. I think that would be the correct interpretation. That, yeah, well, one way to think about it is this is what governs the parameter value's probability based off of the data.
Mhm.
And this weights it, so it makes it really small, the probability, or really big, the probability. And yeah,
I was just wondering. I don't know if it was even,
No, that's a
proper.
great question. I thought I had the answer off the top of my head, but I'm not entirely sure. I would assume that it does. Somehow it makes it so that these probabilities don't get too wild, so to speak.
Yeah,
That
you'd
would
have to
be
if that was
best.
part of the algorithm, yeah.
Yeah, but that's a good question.
Thank you.
Okay, so let's run this thing. This should only take a little bit of time, like 30 seconds. All right, so now we have our posterior. What does this look like? And you'll see it's all filled out. Looks nice and pretty. We have our intercepts, slopes, standard deviations from the MCMC, as well as whether candidates were accepted or rejected. Okay. And now we want to go through diagnostics. We want to make sure MCMC looks good. So generally speaking, you'll do this with looking at trace plots. Trace plots are just plots of the parameter value on the y-axis as a function of the iteration on the x-axis. So here, the very first set of plots show the full MCMC chain. So you'll notice that the initial value was not very good that was picked, and that at the very beginning of the chain, it jumps around wildly and then kind of converges over here. We actually don't want to look at trace plots like this, because we really don't care what happens at the very beginning, because that's not when the MCMC is at its equilibrium point. We want to focus on that equilibrium point, which is in the latter half of the chain. So you'll notice with all of these plots, they jump quite a bit until they settle somewhere. With the scaling, though, we don't know if these actually look good. They could be terrible, but it just jumped around too much at the very beginning. That's where the burn-in comes into play. The burn-in is just, we say, the first X number of iterations are no good, so we'll remove those. For this, I went with the first 25%, the first quarter, which is what this code does. And I'm just going to filter out those iterations, remove them, and then that's what I want to look at. So these are the trace plots that are much nicer looking. And this is what you want to see. You'll see the description is you want to see a furry caterpillar. Brett, what's up?
Yeah, is the burn-in just arbitrary based on what you see on the plot, or is there something that you're doing with numbers to determine what that is, or where that stops?
That's a hard question to answer because I think everybody kind of has their own preferences with it. It's a good question, and unfortunately, I don't have a good answer. I chose 25% because I think that's generally what I see others doing, and that's how I base that number off of. I'm not entirely sure if that seems like a plausible thing to do, is look at this trace plot and say, okay,
Yeah.
the first quarter doesn't look very good, so let's take those out. I do it based off of just, I see a quarter is what I most commonly see. I've seen others do the first half, which seems a bit excessive. I've also seen others do like the first half of 100,000 iteration chain, which is huge. It there's kind of a weird point in my personal opinion that if it takes 100,000 iterations to get to an estimate, there might be other issues kind of going on. And you'll notice that it actually seemed, you could look at this a little more, you could look at how quickly it gets to that point. Might be within the first couple hundred that it gets to the equilibrium point, and then it's fine. So, yeah, I'd say a quarter is probably good, but yeah.
And could I also like follow up with that? So it sounds like the more you cut off, like the more conservative you were kind of being, but at the same time, it might be that you were like being like too conservative or like overfitting if you cut off too much. Is that kind of like a good way to like summarize the balance? Or is that like a misconception of how to think about this?
Yeah, I'm not sure. I guess I don't know about cutoff. If the more
Okay.
you cut off would be more conservative.
Uh,
I honestly can't speak to that.
okay.
I do think more iterations is sometimes interpreted as more conservative.
Mhm.
Again, I think there is a point where you can kind of go overboard with the number of iterations. I think 100,000 seems like a lot.
Okay.
Of course, that depends on your data, and it might just take a very long time to converge.
Mhm.
So yeah, sorry, I don't have great questions for,
No, that's
or
okay. It wasn't a
great
very direct
questions.
question. So
Yeah, well, in this is truly where, and I'm sure you've always heard that, oh, statistics is more art than science. With Bayesian modeling and like MCMC, this is really where that comes out. And where it can really make you very uncomfortable, or at least it does me in some ways. But that's what the review process is for. And it's also kind of interesting. You'll see in some articles, I think that's also where it's helpful to be very forthcoming with the problems you ran into your analyses. With Bayesian modeling, I've noticed very frequently I will read, this didn't work, so we had to do this thing, which if they hadn't mentioned that, I would have been like, that's weird. Why would you do that? But it's very common with the Bayesian modeling world to say, this didn't work, so we did this, and that helped the model converge. And I appreciate that being very straightforward, because even in the frequentist world, you run into those problems. Like the LME4, I used to run into issues all the time with that package. But it wouldn't, I'd only gloss over it in the actual paper. So yeah, that might have been a tangent. Whatever. Okay, but these look good. So you want them to look like a furry caterpillar. A friend of mine who took statistics had a professor who, with an assignment that you submitted trace plots, and all he wrote back was furry. And I thought that was the funniest response to an assignment, so I decided to throw that in. Kind of weird, I thought, but it was funny. Okay, so if your trace plots look good, that's awesome. If they don't, a very good place to look is your acceptance rates. This is another not hard and fast rule, but if your acceptance rates are between 25 and 35%, that's considered pretty good. And so here, because they consist of, the acceptance columns consist of ones and zeros, where one is acceptance. We can just take the mean of that, and that gives us the proportion of samples that were accepted. And that's what this code does, is it just makes all that. So 35, 31, and 27% are our acceptance probabilities. So that's pretty good. And that's not what they were when I initially started this. And then this is where the tuning parameters come into play. When the tuning parameter for the slope was 0.5, it, oh, I can't remember what the acceptance rate was. I think it might have been too high. I have it written here, I believe. Basically, the acceptance rates were a problem because the tuning parameter just wasn't very good for the slope coefficient. And that's because we're working with years, and the scaling of years just doesn't work with that big of a tuning parameter. So that's why you'll notice I changed it to 0.05. When we get to the what next section, I do recommend messing up those tuning parameters, because then you can see what that does to the MCMC, and in particular, you'll see it in the trace plots. Yeah, okay. And then, of course, you want to summarize your posterior distributions. This is where you can get your point estimates. I like to use distribution plots because I think they look kind of compelling in papers. Here, because I know the true value of these parameters, we can actually compare them. So the solid line is the true value for the intercept, or sorry, the dashed line is the true value for the intercept. The solid line is the estimated value for the intercept. That's the posterior mean. We see here it does a decent job. It's not perfect, but it does a decent job. You will notice that all of the estimated values are closer to 0 than the true values. That's partially because of our prior. Our prior draws it slightly closer. We use such weakly informative priors that probably didn't actually affect it as much. But if you set more and more informative priors, lower that standard deviation, you'll see this, your estimate really get drawn closer to 0. So we have the posterior distribution for the slope, the standard deviation. So that's a little more off, although the scaling here is pretty tight. And then you can calculate summary statistics. So your posterior means, those would be your point estimates. So what you'll see for like the from the LM function, if you're using frequentist statistics, that's generally what the posterior mean represents, is that intercept. And then, of course, you want to figure out, is it significant, how meaningful it is. Here, I did that with interquantile intervals, 95% interquantile intervals. These are just the boundaries for the inner 95% of that posterior distribution. This is technically not what you want to base your inferences off of. You generally want to use highest density credible intervals, which more closely align with confidence intervals. And so I note a package here, HBayes DM, and a function where you can calculate those. They are very similar to the interquantile intervals. So I just did that here, just for the sake of simplicity. And they'll generally always be pretty similar to one another. So we have, for the intercept, here's our mean interquantile intervals. We're really interested in that slope coefficient though, because that's what our predictor is. So the coefficient, the posterior mean for the slope is -0.29. Here are the interquantile intervals, and notice that that does not encompass 0. So you could consider this a significant effect, so to speak. We also have the standard deviation. Not going to worry about that. It seems to do a pretty good job. Our standard deviation, the true value was 1. It's pretty close to that. We can compare these to the frequentist regression. I have a plot of the frequentist regression, but that shows this a little bit better. But basically, our Bayesian estimates are very close to the frequentist estimates. And that, oh yeah, that's here. So I like to plot predictive values. So here's our data. So we have our log elasticities as a function of year. There is a black line, believe it or not, that shows our Bayesian regression line. So I use that posterior mean for the intercept and slope to generate that line. And then I also compare it with a frequentist regression. You can't see that black Bayesian line because the frequentist red line is right on top of it. So our Bayesian regression does pretty good, I would say. And if you look at the conclusions would be identical in terms of significance. And you'll actually find that pretty frequent, that the Bayesian and frequentist inferences are pretty close to each other. Yeah. Okay, so that's all I have, essentially. I do recommend a few things. One is breaking the MCMC, is what I call it. And what I mean by that is tweak with the priors, tweak with the tuning parameters, and just set them, set the standard deviations on those priors really high, really low. Same with the tuning parameters, make those really high, really low. See what that does to the MCMC chains. Particularly, how does it affect your inferences? How does it affect the parameter estimates? And then also, if you'll remember, the data contains a variable called sex that you could add this to the code I have above, the MCMC, to see whether sex plays a role in elasticity of demand for fentanyl. And I did post code for how I did that, but I do recommend seeing if you can modify it for yourself. Okay.
For the sex variable, is that like adding it into the model or having it be a completely separate model for the elasticity?
Sorry, say that again.
Is it being like a completely separate model, like its own, like just B0, B1, or is it adding an additional variable into the model?
I would add it in the model.
Okay.
To turn it into a multiple regression. You could actually just substitute it as well, but I would recommend adding it in the model. And that, I mean, you're basically, you have to go, where the heck do I do that? Oh yeah, gosh dang it, get lost. You're basically just adding it as one of these little sections here.
Yeah,
You could
it would
just
be
add it.
B2.
Yeah.
Yeah.
Of course, you'll want to change your likelihood. You'll need to add a prior. You'll need to do all of these things to incorporate it. But it would be a cool way to test your knowledge. And I have the code for how I did it. So you can
Yeah,
also.
that was actually my next question, is how would you do it as a multiple regression? So that's perfect.
Yeah. And the simulation code's also up there. So another thing you could do, I didn't even think of this. You could tweak with the simulation code and just change those values and see how well the MCMC actually captures these different things. Might be interesting.
Yeah.
Yeah.
And we also, in case anybody hadn't seen it, Jeremy had included a multiple regression script, which we have in the directory. It's labeled as like supplementary, but we have that there as well.
Awesome. Is that
Can you guys hear me, or is the music just too loud?
No, we can hear you.
Oh, I just wanted to say, sorry again, I was like, I just wanted to say that this was such a cool resource for me, especially to have within our department. I think people are like itching to get into Bayesian modeling and kind of don't know where to start. Like obviously there are some advanced techniques here. But as someone who got into Bayesian modeling last year, your approach is much more inclusive and thoughtfully designed. That's where I started. It's super, super cool. And I think we're gonna hopefully move in this direction a little bit more within our department moving forward. So just wanted to give you a shout out, and as Billy said, for answering everything so clearly. This is super cool. Thank you.
Yeah,
Cool.
it was very thorough.
Cool. Well, thank you. I missed part of what you said, Stephen. Sorry. I think I caught the gist of it though. Yeah. And I'll be honest, I consider myself a very practical modeler in terms of there are some things mathematically speaking, I don't fully understand it, but practically speaking, I try to make sure that it's useful is how I approach these models, is how useful are they in understanding your data. And I think that can be a very helpful mindset to have. And it wasn't me learning Bayesian modeling. Gosh, I first wanted to learn about it 8 years ago. And I don't think the first paper I published using Bayesian modeling was this year. So it took me a long time, but I do think, but that's partially because there wasn't an environment for it. I had to take a Bayesian modeling class from the ecology department, and they're wonderful. I'm not trying to diss ecologists, but their questions are radically different than ours. And so it's hard to make those translations. So yeah, hopefully y'all can get a bigger crowd going.
Could I ask, I think you might have said it before we actually started, but I remember one thing that I think you said was that some people who like want to do this sort of thing in the field have like moved on to like other techniques, or there might be other techniques that are like similar to this. Could you speak to like what those might be, or like what might be kind of like relevant to this?
Right. Yeah. So I'm glad you brought that up because yeah, Metropolis sampling is not really what you want to be doing. I hate to say it, like I don't mean to be like, oh, everything you just learned is a waste of time.
No, not at all. Yeah.
The reason why I did want to teach is, for one, I actually know how to do this. I don't know how to do really fancy MCMCs, but this was the way I was like, oh, now I kind of get how some of this, what we're actually doing, which was so frustrating to me. But there are much more complex and much better MCMCs out there. And I think you had posted some. Stan is a programming language that uses Hamiltonian Monte Carlo algorithms. And that is a much better MCMC than Metropolis sampling. And so this stuff has like progressed way beyond the very basic Metropolis sampling. That's of course where it started, but now there's more complex ones. So
So they're all still like in that same MCMC family. It's just like slight deviations on that.
Yes.
Okay.
Generally speaking, the deviations are in how they generate candidates,
Okay.
and how they determine the probabilities associated with those candidates. And that gets in, oddly enough, apparently geometry gets circled back in there, which wouldn't have expected.
No, I wouldn't have.
But yeah, there's Hamiltonian Monte Carlo, which is what Stan uses. JAGs use Gibbs sampling, which is a variant of Metropolis MCMC. I like Stan personally. Programming in it can be aggravating, but it's pretty efficient, I would say. It's really good for hierarchical models. Because like you saw here, the frequentist, like I would never be like, oh yeah, I built an MCMC to run this Bayesian regression to look at, fentanyl as a function of year, because it generates the exact same answer as the simple linear regression. Like we just generated like a couple thousand lines of code for something that you could have done in one. But once you start doing more complex models, then you'll really want to start doing more intensive MCMCs.
Mhm.
And that's also where it'll start deviating more and more from the frequentist approaches, or where those approaches aren't even existing. Yeah.
Okay.
Sorry.
Yeah. No. The examples I put on the thing. This was my first time ever working with MC, and even like hearing of them. So I was just like trying to Google. Like I do know I had seen that they were involved in FSL. Like I think that was the first time I ever actually saw the acronym. So yeah, all those things they put up there, I was like, it says that there's an MCMC involved. So just so somebody has a reference, I guess.
Well, and you know, the weird thing is, so kind of going back to the ecologists,
Yeah.
they actually do program their own MCMCs. And they'll use other languages like Stan and whatnot, but they also just program their own MCMCs to answer some weird, not weird, I should say, but some question that
Very
they
specific
have.
question.
Yeah, and they, of course, know their MCMC programming skills are way beyond mine because I don't need to know some of that. But yeah, you'll see it in a lot of different applications that they'll just write their own MCMCs. And you're like, wow, okay, that's pretty interesting. Yeah. I will say, because Brett, I don't think you were on before, and this might be helpful. I do think Richard McIlrath's book, Statistical Rethinking, and he also posts lectures on Bayesian modeling. I think that is one of the best sources out there, I personally think. It won't go into some details that you might like, but I do like some of the really nitty-gritty details of the programming itself. But I do think he provides an awesome conceptual understanding of Bayesian modeling and just modeling in general. Even if you don't use Bayesian modeling, that book I find very helpful in thinking about your data.
Jeremy, would you mind posting his name in the chat?
Yeah. I'll actually have to find it because I can never remember how you write it. Because it is kind of weird. Oh, I have chat open. And he has a YouTube channel where all of his lectures are available free. And I went through them a while ago, but I'm pretty sure he has some as recent as 2023, maybe even this year, of walking through each chapter of his book. And I imagine they only get better as he teaches this stuff more and more.
All right, cool. Any other like last questions before we finish up? All right, cool. Well, yeah, again, thank you very much, Jeremy. This was an incredible tutorial workshop. Very happy to like have it in our collection.
Thank you.
And yeah, thank you very much.
Yeah, I appreciate y'all.
Thank
Take it
you.
easy.
Jeremy.
Call it a day there. Thank
Thanks,
you.
Jeremy.
So feel free to email me if
Oh.
you have any questions.
Okay, sounds good.
See y'all.